Okay, very quick review. We just said yesterday, recall that we improved our definition of a two-sided limit, a regular limit, to involve the one-sided limits from the left and the right. So the limit of f of x as x approaches a is equal to L if and only if the limit of x as x approaches a from the left is equal to the limit of f of x as x approaches a to the right, and they're both equal to L. Okay. And we just said this is the last one we ended up with, discussed in terms of two-sided limits. Well, okay, so we talked about these in terms of infinities, which eventually that's how we want to do it. But for now, technically, we probably should also say this. Those are all examples of DNE. Okay. I think it's safer, though, on the AP test, they'll accept either one. If you're confident in your answer, positive infinity or negative infinity, I think it's always better to use those. Yep.
So anytime that it's DNE, it would be infinity.
Well, we're going to talk about those today. There's three different places where limits won't exist, and we're going to talk about that today. Yeah, so good thing you brought that up, Jonathan. How about that? Oh, actually, that's not quite the slide. It's the next slide. So there are three approaches to evaluating limits. We've talked about up through today, or through yesterday, we talked about numerical and graphical approaches. And today we're going to start to talk about an analytic approach. Okay. The advantage to an analytic approach is that it gives us exact answers, right? So first of all, let's talk about places where limits don't exist. So limits fail to exist in three different instances. One of them is different behavior from the left and the right. So we could call that maybe a gap in a function. And here's an example. If we take the function f of x equals the square root of x over x, and I want to do one, gosh, I don't want to spend too much time on this, but now is maybe a good time to introduce something. What do you do when you encounter absolute value functions? Okay, because they're a little bit problematic in that they're different, right? They're true. I mean that's the definition of what is the definition of the absolute value of a? It's really this. The absolute value of a is just equal to the square root of a squared. That's the definition of the absolute value of a. But that's not very useful when we're trying to do analysis on a function, because that's still a pretty complicated looking graph. Recall that absolute value functions have V-shaped graphs, right, if they're linear functions, okay? So what's always helpful here, whenever you experience, like you're dealing with or you're forced to reckon with an absolute value function or a piecewise function, it's already written that way. But we want to write the absolute value function as a piecewise function. Piecewise functions are easy to deal with piece by piece. So the working definition, the definition we always fall back on when we're doing analysis, when we're either graphing or trying to analyze a function or explore the behavior of a function, is this one. The absolute value of a is equal to the piecewise function. It's equal to a, where a just really represents the argument of the absolute value function, meaning whatever's inside it, right? Whatever's inside the absolute value function just equals itself in the case that it's positive valued, okay? That whatever's inside is greater than 0. Wherever that's true, for whatever part of the domain that is true, the absolute value function does nothing. Easy way to convince yourself of that is answer the question, what's the absolute value of positive 2? 2, right? Doesn't do anything in that case. Now, what if what's inside the absolute value function is negative valued at a certain input, at a certain value of the variable x, presumably? For a value of x where whatever's inside is negative, we have to take its opposite to make it positive. That's the job of an absolute value function, is to always output a positive value, correct? Okay, and then there's the in-between case. in between positive and negative values of the argument is the value when it's actually equal to 0. And in that case, the absolute value function returns a value of 0. Okay. This is a good way to do it because when I want to later on even do like calculus, this isn't going to mean anything to you now, but if I'm differentiating a function or something, well, now all I have to do is just differentiate that piece on that domain, that piece on that domain, and it's easy because these are easier functions to deal with than the absolute value function. The individual pieces are, okay? So what about this function here that we're working with? The f of x equals the absolute value of x over x. Okay, well, the absolute value of x, rather than rewrite this whole thing, I'm just going to do this. I'm just going to make this, oh, thanks, that was kind of a big eraser. Let's do that instead. I'm just going to make these x's for now. So we've already defined this function then. The absolute value of x equals x when x is positive, negative x when x is negative, and 0 when x is 0. Okay? So then what's that mean for this function? Well, all I've got to do for this function then, this new function f of x, is write it as a piecewise function. Well, if this is the definition of absolute value of x, then f of x would just be these pieces each divided by x, right? So I'm going to get when x is greater than 0, when it's positive, I'm going to get x divided by x, right? Everybody see that? Give me thumbs on that. Does that make sense? So if this is my function, then the absolute value of x is being replaced by that piecewise function, right? Okay, so in the event that x is greater than 0, the absolute value of x is equal to x, right? So then what's that leave me with? That leaves me with absolute value of x is now x, so I get x divided by x, which is 1. Okay, make sense? Okay, in the event that x is negative valued, well, then the absolute value of x is equal to, in that instance, negative x. And so f of x is equal to negative x over x, which is negative 1. Okay, now what about when x, I'm not giving myself enough room, am I? I better do this. Oh, man, there we go. Scoot that down a little bit. And if x is equal to 0, I would get 0 divided by 0, but I can't do that. We can't divide by 0, right? And so that tells me that for f of x, x cannot equal 0. Okay, make sense? So then we get this simplified version of our function that just says f of x, which is the absolute value of x over x, just equals 1 when x is positive valued and negative 1 when x is negative valued, which is that graph. Yep. Because if x is equal to 0, then when x is equal to 0, the absolute value of x equals 0, right? Well, our function is absolute value of x over x. If we're choosing to evaluate this function at 0, so in other words, this is really what I'm saying. Take a different color here. F of 0 then just equals absolute value of 0, which is 0, right? Okay, which we can't do. Yes.
Can you just go back down?
Yes, I can. You bet. Yep. Okay. And look, that's actually, there they have it right there. Okay. So all that stuff I just did up there, That's summarized a little more succinctly up here in the notes, but I wanted to take you through the steps. Yes, sir.
I think the only part that I didn't get was the absolute value part.
This part, right,
When you started making the piecewise function for it.
for right here,
Yeah.
that part. Okay, this is new to you guys, but this is what we always want to do. If I have the absolute value of anything, in this case, it's just x, but it could be some complicated expression. Maybe it's x squared minus 3 or something. If it's x squared minus 3 or x, the pattern's the same. The absolute value of hand, I do this a lot in calculus, hand meaning whatever's behind my hand, who knows, is equal to hand whenever hand is positive for the values of x that make it positive. Okay, it's equal to negative hand whenever hand is oh man, I don't want to do that. Whenever hand is negative, and whenever hand is equal to 0 behind my hand, then the absolute value function equals 0. That's the behavior of any absolute value function. When I evaluate the absolute value function and what's inside is positive, it has no work to do. It's only when whatever's inside is negative that you got to multiply by -1 to make it positive. Does that answer your question? Okay. So given that, I mean, that gets us to the point where now we can see what the graph is doing. Okay. So given the graph, it's a pretty easy thing to reckon with here. We can obviously see that this limit can't exist because the limit of this function as x approaches 0 from the right is 1, but the limit of f of x as x approaches 0 from the left is -1. They don't agree. The one-sided limits don't agree. So the two-sided limit doesn't exist. Okay? Give me 1 to 5 on that. Does that make sense? Okay, so any place where we've got different behavior from the right and the left, and we didn't have to pick such a complicated one here, but I just wanted to introduce you to that idea of how do you deal with absolute value functions. We'll go through that several more times. Like later on, we'll deal with more complicated absolute value functions, and we'll go through it again. I promise. But this could be an easier function too. This could just be a piecewise function where there's a break. Okay, where you're given a piecewise function. Okay, so that's one place where there's a gap in the function, different behavior from the left and the right. That's one place limits do not exist. Another place is unbounded behavior, asymptotes, like we looked at yesterday. Yes?
Real quick for the last one.
Mm-hmm.
Do one-sided limits still exist?
Yeah, they did, right? The one-sided limit from the right is 1, right? Doesn't that make sense? Because an ant walking towards x equals 0 from the right anticipates stepping on 1 when he gets to 0, right? Okay, so that limit exists. The limit from the left also exists, but it's different. That's why the limit doesn't exist. The two-sided limit doesn't exist. Okay, the one-sided limits did. The two-sided limit, and when we say, okay, which brings up probably another, I should probably mention this. When mathematicians talk about limits, are they probably talking about two-sided limits or one-sided limits? Two-sided limits, because if you're talking about a one-sided limit, you're specifically saying one-sided limit or limit from the left or limit from the right. Okay. So unbounded behavior would be any place where you have an asymptote. And that's pretty obvious that the limit can't exist there because the function doesn't even exist there, right? Well, okay, that's a bad thing to say because limits can exist where functions don't exist, like that last example, right? The limit from the right is 1 even though the function doesn't exist at 0. Okay, but this is a different kind of not existing. This is an asymptote not existing, right? There can never be a limit on this one because there's no value you could ever point to and say that's what you're approaching, right? Because infinity is not a value. Infinity just is a concept, right? You can't treat it like a number. Okay, so there's another type. And by the way, unbounded behavior doesn't have to be consistent on both sides. We could have something like this, which we call a cusp. Well, actually, that we don't even call a cusp, but we'll see a cusp later. Something like this where we get behavior that's positive on both sides, but it could be split behavior too. It could be diving down to negative infinity on the left and positive infinity on the right. Doesn't matter. Either way, if there's an asymptote there, the limit doesn't exist. And then the third kind is really weird. You don't see this very often at all. This is oscillating behavior. Okay, and I have something set up to show this to you. I set up this really cool Desmos file that's, if we have time, I'll do it, but I just really don't want to. Sometimes I have to discard some of my really cool stuff I've built if we're going to stay on this schedule, but we'll see. So what is this though? This oscillating behavior. This is a good function to consider. The sine of the quantity 1 over x. Okay, now why is that such a good? You know what? I can't resist. I'm going to show this to you. This is pretty cool. I got to zip up here a little bit. So I'll be quick about it. Okay, but if we go to look at this Desmos file, and if I can think of it and I have time, I'll make a running file of all these, like a Google Doc that's got links to all these Desmos files if you want to look at them. So let's take the regular function, just y equals sine theta. Okay, what's that look like? Well, it looks like that, just a sine function. Okay, now what if we do something different? What if we define a new function, y equals the sine of a times x? Okay, this is a composition of functions because now I'm taking the sine of the function a times x, right? Well, what's going to happen if I make a bigger? Like if I make a 2 or 3 or something, what's it going to do to that sine train? In this case, it's 1, but what if I change it? What if I make it 3? Does it make, okay, so my question is this, is it going to compress the wave train or stretch it out? It's going to compress it, good. And if you see that, that's good. It's going to compress it. How come? Well, here's why. Here's how you can think about it. Because these are compositions, right? The sine function is being fed values by the interior function, ax. In this case, 3x, right? What do sine functions do? Functions are just like machines. They gobble up input values and spit out output values, right? We know that when the values range from 0 to 2 pi, the sine function will have gobbled up a complete sine wave. It's gone through one complete cycle of sine. It's gone one lap around the unit circle, right? Well, what if I'm multiplying those angles inside by some number, like 3, right? Doesn't that mean for any x value that I choose, when I multiply that x value by 3, all of a sudden it's accelerated the angle inside from, like, for example, if x is pi, right? Well, if I multiply pi by 3, now it's 3 pi, right? So instead of going from 0 to pi, the function is now seeing something, the angles change from 0 to 3 pi, right? Everybody get that? Because when x is 0, 3 times 0 is just 0. So the two functions are going to overlap there at 0, right? But by the time theta has gone from 0 to pi, which would be half of a cycle normally, now this new function has gone from 0 to 3 pi. So it's oscillated a bunch more, right? Does that make sense? Okay. So then let's try something different. So what if we instead, let's turn this guy off and let's try something like, how about the sine of x to the b? Okay, well, if b is 1, then they look the same. But what's going to happen if I make b like 2? What's that? Can you predict what that wave train is going to look like then? Now we're taking the sine of x squared. Okay, but yeah, that's true, partially true. But it's going to have two different behaviors here. Because think about x squared compared to x. The negatives are going to be, yeah, they are. The negatives are going to be flipped. You're right. So it's going to do that, but it's going to do one other thing. Now think about x squared compared to x. For values of x between 0 and 1, x squared is actually smaller than x, isn't it? Because 0.1 squared is 0.01, right? When x is equal to 1, x squared and x are exactly equal, so the functions should overlap at that point or intersect. But then for values of x greater than 1, now x squared starts to take off non-linearly, right? It's going to get bigger faster. So we should expect to see then, shouldn't we, that this function is going to be kind of stretched out between 0 and 1, but after 1 it's going to be compressed, and the rate of compression is going to change, right? The bigger the value of x, the more x squared has deviated away from x, right? Because I think about 2. X2 squared, 4, is not that much bigger than 2. It's only twice as big, right? Put in 10. 10 squared is 100. Well, that's 10 times bigger, right? So the bigger x is, the more that x squared has deviated away from the regular angle x, and so the more compressed the function is going to be. Do you have to get all this stuff perfectly? No. I just want to give you a glimpse of this. Is kind of interesting and useful to start to think about functional behavior a little bit. So look, if I drag this thing out to 2, look what we see. Okay. If I drag it out to 4, it'll be exaggerated. Okay. Yes.
So is it basically like a, well, not basic, not the same thing, but sort of like an exponential?
Well, it's
It starts off slow.
well, it is. It's just like a quadratic or a cubic function, right? Think about that. Like a quadratic function starts off slow and then it picks up, right? But the quadratic function is just producing the angle that the sine function sees. So the sine function is just going to oscillate more and more rapidly as that angle starts to increase more rapidly, right? Because sine functions, they just keep repeating over and over again, right? And so finally then, now let's look at the last one. Well, you tell me. I guess we can skip through. What's going to happen to Okay, so how about sine of x to the c, where c is 1? Well, now it stays the same. What's going to happen when I make that x to the negative 1, which makes it a 1 over x? Think about the behavior of 1 over x now, right? X squared got bigger as x got big, right? 1 over x, that's an inverse function or a reciprocal function. A reciprocal function, 1 over x, when does that get big? Like if I just graph, I tell you what, let's just look at the function 1 over x. Let's just look at the function y equals 1 over x. Turn everything else off. Well, that function gets small as x gets big, right? It approaches infinity as x approaches 0, right? So where is this function going to be compressed and where is it going to be stretched? It's going to be compressed in the middle, isn't it, right? And in fact, how compressed is it going to be? Well, as the value of x, if we're taking the sine of 1 over x, as x approaches 0, I mean, look at those values. The values of 1 over x get infinitely big, right? So then, is that a possible function to ever graph? You couldn't ever graph it, right? You couldn't graph it for a couple reasons. There's some interesting reasons. You couldn't graph it because there isn't sufficient acuity in the graph. The resolution isn't high enough, for one thing, right? But the other reason is because it would take, like if I'm going to draw this on the board, it would require an infinite number of ink for me to graph that function, right? Because as I move back, what's the function going to do? Well, it's going to start, when it gets to over here, it's going really slowly. But when it gets to 1, inside 1, it's going to start to oscillate faster and faster and faster as I move backwards towards x equals 0. So here's what it looks like. If I graph that function, there it is, right? I can zoom in on this thing and kind of get a sense, but pretty quickly, Desmos would start to break down if I tried to go in too much further, because it just can't draw that stuff. If I tried to draw it with my pen on the board or with a pen on paper, I could never do it, because it would require an infinite amount of ink, because there are an infinite number of oscillations there, right? So therefore, I could never calculate it even electronically exactly correctly, because it would require more bits of information than the universe has the capacity to sustain. The universe there's only so much information, it's equal to the entropy of the universe, that could ever be stored in the universe, and that's not enough to make the calculation. So for many reasons, it's impossible to do this. But we can just think about it this way, because there's no value that the ant ever approaches, right? That poor ant, as he walks backwards from x equals 0.5 towards x equals 0, every step he takes, every little itty bitty ant step, after a while, he's just going up and down crazy. He's never going to be able to, he doesn't have any idea what he's approaching. He's oscillating uncontrollably as he gets closer and closer and closer to 0, right? Get the idea? So those weird oscillating functions, that limit can't exist, right? Can't exist. And the function doesn't even exist at 0, because again, I've got a 0 on the bottom of a fraction, which is, we can't do. No, it's not. The limit's undefined, because, because there's no end to the oscillations, right? This would be a good proof, right? If you were to take these successive fractions, let's just take 2 divided by successive odd multiples of pi. 2 divided by 1 pi, 2 divided by 3 pi, 2 divided by 5 pi, etc. Well, all of those values give me back the same output. They all give me back, they give me back opposite outputs, oscillating outputs. If I've got like the first one's going to be 1. I'm not going to try to define this any more carefully. It's going to sound confusing. But the first is 1, negative 1, 1, negative 1, 1, negative 1. It just oscillates back and forth forever, right? I could do this indefinitely, because these fractions are just getting smaller, aren't they? If the top is staying 2 and the bottom is growing, that means the fraction is diminishing. That'll never end, right? So there's your proof. If that's the behavior that's always going to happen, there's where could you ever end up? Nowhere. Yep.
Does it only happen when x is approaching 0?
Well, in this case, when x is approaching 0, it could have been like, I could have written a different function. What if it was 1 over x minus 2? Then it would be when x approaches 2. Okay, but you see the same thing. Okay. Okay, so the technology pitfall is that graphing technology can't do that. So don't think just because it doesn't look like it's doing that it's not. It is. There's just some limitations to the graphic processing capacity of a graphing calculator, for example, or Desmos for that matter. Okay. So, summary. The common types of behavior associated with the non-existence of a limit. In other words, limits do not exist in these 3 cases, where f of x approaches different numbers from the right and the left, where it increases or decreases without bound, aka vertical asymptote, or it oscillates between 2 fixed values as x approaches c. Okay, and there are some pretty, like this Dirichlet function is really very interesting. I don't want to spend more time on this, but what if you define this function where f of x is equal to 0 if x is rational and 1 if it's irrational? This is a function that has no limit at any real value of c. That's crazy. You can't take a limit any place in this function. The limit exists, or the function exists, it's defined, but there's no limit anywhere. Okay? Because you can't approach, you'll never approach a value from an adjacent point that is continuous with that point. And we'll talk about that. What's that? This function right here. Yeah. There's no value, there's no input value, no value of x. where this function, you could ever take a limit. It doesn't exist anywhere. It's that function. It's that piecewise function.
Oh, it's just two different values.
Yeah. It's just going to oscillate between those values, but it oscillates every time. I mean, it oscillates infinitely, right? There's,
So how could you, if you graphed it, would just be two dots? Right?
it would just look like, well, I mean, it wouldn't look very interesting. It would just look like this. But I mean, it would look like two, from your perspective, it would look like two horizontal lines. Yeah. They never overlap vertically, but they're just constantly oscillating back and forth.
Oh, I see. It's fractional.
Okay, so this will make more sense when we'll be able to introduce a new vocabulary term that makes this all way more clear, which is continuity, which we haven't talked about yet. But later on, you'll be able to revisit this and say, oh, okay, man, now that really makes sense. So let's try this. Use the graph of G in the figure to find some values. All right, so what do you think? Let's take a second, look through these. What do you think? What's G of 1? G of 1 is 4. Yeah, go ahead and just show me fingers on these. G of 1 is 4. Good. So B, what's the limit of G of x as x approaches 1 from the left based on that graph? Yep, good. 2. Okay. What's the limit of G of x as x approaches 1 from the right? Okay. Limit of the function, and that's the function in the graph, as x approaches 1 from the right. So the ant's walking along this line, this part of the function right here, towards x equals 1 from the right. Where does he anticipate stepping? 4. Good. Okay, so it's 4. So then, here, I'll tell you, let's write these answers down. How about? So you guys told me this one was 4, right? This one was 2. This one is 4. What's the limit of G of x as x approaches 1? dne. What's G of 3? 1. What's the limit of G of x as x approaches 3 from the left? 4, right? Everybody agree? It's right there, isn't it? It's 4. That's the limit. Limit of G of x as x approaches 3 from the right? 1. So yeah, so they didn't. So the limit wouldn't exist there, right? They didn't ask that. But the limit of the function as x approaches 3 would not exist. What's G of 4? What's the limit of G of x as x approaches 4? 2. Yeah, because in this case, the ant actually ends up stepping where he thinks he's going to step, right? The limit asks the question, where does the ant anticipate stepping? At y equals 2. G of 4 asks the question, where does the ant actually step? What is the value of the function at 4? And it's 2. Yep. Okay, when you're approaching, so is the question, like, are you worried about if I'm approaching 1, about starting over there or something?
Yeah.
Okay,
So
so
you said you're approaching from the right. Would
yeah.
you start from 6?
It doesn't matter where you start, but when you're talking about the limit, you're only talking about values arbitrarily close. So you're going to be, so these values, you definitely would want to be in here, right? And it sounds hokey. You want to be, yeah, essentially you want to be so close to when you take the limit, the idea when we say arbitrarily close, means you can get as close as you want to, right? Like, think about this. If we're talking about my behavior of me approaching the door where I cut my distance in half every second for the rest of my life, do I have to start clear over on the East Coast or so? I don't really have to, right? I can just start close to the door and you get the behavior, right? If there were some other impediments in between, we wouldn't want to go. That would just complicate things. I want to start where I can just look at specifically at the behavior of approaching the door without having to worry about that darn wall there, because I'd probably have to walk into the room and walk over to the wall, right? That part's weird. Does that make sense?
So.
Yep. Yep. Go back. Yep. Mm-hmm.
So there doesn't actually have to be a limit, because for like I, the limit doesn't actually have to exist for that to be where X is.
Say that for what to work, Maria. I'm not sure I understand.
Like it equals 2.
Yeah. It equals 2 because the ant anticipates stepping at a y value of 2. Oh, he could step somewhere else. Yeah. It doesn't matter. Like there could have been, for example, there could have been a hole in the function there, right? We could have had something like this where there's a hole in the function there and the point's actually up there, right? In which case the limit would have still been 2, but now the value of the function would have been 5. Are H and I, where's H? Oh, right here, yeah. H and I, they're both 2 in this case. They wouldn't if I drew it like this. Okay, but if I don't change the problem, if I leave it the way it was, there is. There is. The 2 are really, the fact that they're both equal to 2 is an accident. They don't have to be. What does this say right here? Let's just focus on I for a second. The limit of g of x as x approaches 4. What's that mean? That means that ants approaching from the left or the right both anticipate stepping on a y value of 2 when they get to x equals 4, which they do. They both anticipate stepping right there, okay? It's irrelevant at that point. As far as the limit's concerned, it doesn't matter if they actually do step on 2. Makes no difference. But in this case, they do, because we can see that the value of the function, there is a point there with coordinates 2, 4, right? The value of the function, what h represents is where does the ant actually end up when he takes that last step. The limit doesn't. The limit just means where does he think he's going to be when he takes that step? Where does he anticipate stepping? Okay? Does that make sense? Okay. Is that it? Oh my goodness. It just goes so fast.